Your head is older than your feet, not as a figure of speech, as arithmetic. Time runs faster the further you are from a mass, so the crown of your skull has been outrunning the soles of your feet for your entire life. And over 80 years, the gap comes to about 470 billionths of a second. Nothing will ever bring the two ends of you back into agreement. There is no procedure for it anywhere in physics. In 2022, a laboratory in Colorado measured that same gradient across a single cloud of atoms, 1 millimeter tall, sitting on a table, going nowhere. But here is the part nobody mentions. When two perfectly working clocks disagree, physics does not tell you which one is right. It tells you the question is broken. By the end of tonight, you will know exactly what has been taken away and why it is far worse than the story about the twins. Get comfortable. Hit subscribe if you're new here, because by the end of this, the number you give when somebody asks your age is going to stop meaning what you thought it meant. Now, let's slowly ease into this. Part 1. The gradient inside you. Your head is older than your feet. That is not a figure of speech, and it is not a way of saying something else more gently. It is an arithmetic statement about your body, and the number attached to it can be calculated in about 30 seconds by anyone who knows two constants. The top of you and the bottom of you have been running at different rates for your entire life. They are running at different rates at this moment, and the gap between them has been widening every second since you were born. The reason is that time passes more slowly, closer to a mass. Not appears to, not seems to from certain angles. It passes more slowly, in the sense that a correctly built clock, placed low down, will accumulate fewer seconds than an identical correctly built clock placed higher up, and when you bring the two together afterward and set them side by side on a bench, the readings will not match. Nothing broke, nothing drifted. They simply counted different amounts. The size of the effect near the surface of the Earth is governed by a very small number. For every meter you move upward, time speeds up by about 1 part in 10 quadrillion. Written out, that fraction is roughly 1.09 times 10 to the minus 16 per meter. It is a fraction so small that our language does not really have a comfortable word for it, which is part of the reason nobody mentions it. Now put your own dimensions into that. If you are somewhere around 1.7 meters tall and you are standing upright, then the crown of your head is moving through time faster than the soles of your feet by about 1.85 parts in 10 quadrillion. That is the gradient. It runs continuously from your scalp down through your skull, your throat, your chest, your abdomen, your knees, and out through the bottoms of your feet into the floor. Every layer of you is on a slightly different schedule from the layer above it. Let that run for a life. 80 years is about 2.5 billion seconds. Multiply the gradient by the duration, and the accumulated difference between the top of you and the bottom of you comes out to something in the neighborhood of 470 billionths of a second, just under half of 1 millionth of a second. That is how much extra time your head will have lived through, compared with your feet by the end. I want to stay here for a moment, because this is the part that gets skipped. Close your eyes, if they are not closed already, and start at the top of your skull. Right there, at the crown, time is moving at its fastest anywhere in your body. Now come down, past the forehead, past the eyes, past the jaw. By the time you reach your throat, you have already dropped through a measurable fraction of the gradient, and the tissue there is accumulating slightly less time than the tissue above it. Keep going. Your heart is beating at a rate slightly slower than the rate at which your thoughts are being assembled, and slightly faster than the rate at which the blood is reaching your hands. Come down through the abdomen, down through the hips. Your knees have been living a marginally shorter life than your shoulders, And when you reach the soles of your feet, pressed flat against a floor that is pressed against a planet, you have arrived at the slowest part of you. That is the piece of you that has aged the least. Not because it worked less hard, but because it sat lower. Now stand up if you are sitting. The gradient just stretched. Every centimetre you added between your feet and your head widened the gap and increased the rate at which the two ends of you diverge. Now lie down flat. The gradient nearly disappears. Lying horizontal puts your head and your feet at almost the same height, which means at almost the same rate, and for as long as you stay there, the divergence very nearly stops. A person who spends their life lying down ages more uniformly than a person who spends it standing. That is a real, physical, measurable statement, and it sounds absurd, and it is true. Here is where most people reach for the word negligible, and here is where I want to resist it, because negligible is not what this is. Negligible means small enough to ignore for a given purpose. It is a statement about your purposes, not about the universe. If you are trying to catch a train, 1/2 1/millionth of a second is negligible. If you are trying to understand what time is, it is not negligible at all, because there is no procedure anywhere in physics for undoing it. There is no operation you can perform on yourself that reconciles your head with your feet. You cannot bring them back into agreement. There is no correction, no resynchronization, no maintenance step. The two ends of your body have permanently different amounts of time on them, and they always will, and the gap only ever grows. That is a strange thing to be true of an object as ordinary as a person, and the same logic scales up through your life in ways that are just as unremarked. Consider two people who are otherwise identical. One of them lives in Denver, about 1,600 meters above sea level. The other lives at the coast. Over 70 years, the one in Denver will have accumulated roughly 5.5 microseconds more time than the one at sea level, purely for having spent their life a little further from the center of the planet. Now consider a third person, a miner working at Mponeng in South Africa, about 4 kilometers straight down, which is close to the deepest place a human being routinely works. Over a career, that person loses something in the region of 14 microseconds relative to a colleague who stayed at the surface. Neither of them will ever notice. Neither of them can ever get it back. There is a version of this that I find quietly remarkable, which is that Einstein wrote the prediction down before anyone could possibly check it. The idea arrived in 1907, in what he later called the happiest thought of his life, the realization that a person falling freely does not feel their own weight, and that being in a gravitational field is locally indistinguishable from simply accelerating. From that one observation, the conclusion follows almost immediately, that clocks lower down in a field must run slow. He published it as a prediction in 1907 and again in 1911. It was 8 years ahead of the full field equations of general relativity and 49 years ahead of the first experiment that could actually see it. For nearly half a century, the claim that your head is older than your feet sat in the literature with no way to test it at all. And it would be easy to file it away as a curiosity, an amusing consequence of a theory, if it were not for the fact that we can now watch it happen directly. This is not an inference from equations. In 2022, a group at Boulder, Colorado, took a cloud of ultra-cold strontium atoms about 1 millimeter tall and measured the time gradient across it. 1 millimeter, not 1 meter, not the height of a person, the thickness of a fingernail. The top of the cloud was demonstrably running faster than the bottom of the cloud, and they resolved the difference with a fractional uncertainty of about 7.6 parts in 10 sextillion, which is the most precise frequency comparison anyone had ever made at that point. To put that number in some kind of human context, a fractional uncertainty of 7.6 parts in 10 sextillion means that if you built a clock that good and ran it from the formation of the Earth until now, 4.5 billion years, it would be off by well under a second. That is the instrument. And with that instrument, pointed at a single millimetre tall cloud of atoms, the gradient was simply there, sitting in the data, exactly the size the equations said it would be. So the effect inside your body is not a theoretical extrapolation. It sits about 1,700 times larger than something we have already directly observed on a table in a laboratory. And that is where the trouble starts. Because once you accept that this is happening across a millimetre, you have to accept that there is no lower limit. There is no distance small enough to be exempt. There is no height difference so trivial that the effect politely switches off. The gradient runs through every object you have ever touched, every room you have ever been in, every atom in your body, all the way down, without a flaw. The obvious next question is what happens when you go the other way? What happens when you stop asking about a millimetre and start asking about a mountain, a planet, a star, a collapsed star, a hole in the ground so steep that the sides never come back up? And the answer to that question is where the word Scarier starts to do some work. But before any of that, we have to deal with the version of this story you were almost certainly given first. Because there is a standard way this idea gets explained, and it is not wrong exactly. It is something worse than wrong. It is comforting. Part 2. The version you were given. Almost everyone meets this idea through the same door, and the door is called the twin paradox. The setup is familiar even to people who have never opened a physics book. There are two twins. One of them stays home. The other boards a ship, travels away at a large fraction of the speed of light, turns around, and comes back. When the traveller steps off the ship, they are younger than the twin who stayed. Sometimes the story is told with a few years of difference. Sometimes, in the more dramatic versions, the traveller returns to find that centuries have passed, and everyone they knew is gone. It is a good story. It has a shape. It has stakes. It has been the engine of a very large amount of science fiction, and it is the reason most people can say the words time dilation at all. And it has actually happened, in miniature, to a small number of human beings. Scott Kelly spent 340 consecutive days aboard the International Space Station, moving at roughly 28,000 kilometers per hour relative to the ground. Across his whole career, he accumulated about 520 days in orbit. He has an identical twin brother, Mark, who is also an astronaut, and who spent that particular stretch on the surface. When Scott came home, the two of them were no longer separated in age by quite the same amount as before. The difference is about 5 milliseconds. Mark's own way of putting it is the best line anyone has produced on the subject. He used to be 6 minutes older than his brother, and now he is 6 minutes and 5 milliseconds older. 5 milliseconds. That is roughly the time it takes a housefly to beat its wings once. It is less than a tenth of the time it takes you to blink. It is not enough to notice, not enough to matter, not enough to change a single thing about either brother's life. And it is completely, permanently real. There is no procedure by which the Kelly brothers can be brought back onto the same clock. Whatever else happens to them, that 5 milliseconds is now a fixed feature of the universe. The same arithmetic quietly applies to less exotic careers. A commercial airliner at 900 kilometers per hour produces a velocity effect of about 3.5 parts in 10 trillion. A pilot who accumulates 20,000 flight hours over a working life picks up a velocity deficit of something like 25 microseconds from the speed alone, most of which is then handed back, and more by the altitude, because being 7 miles up runs the clock fast. Every long-haul crew is quietly playing both sides of this equation on every rotation, and the net result is a number of microseconds on a life that nobody will ever measure. So far, this all sounds tidy. Two effects, both understood, both tiny at human speeds and human heights. The first one, the velocity effect, came from Einstein in 1905, and it is governed by a single quantity that physicists call the Lorentz factor. It has a very particular shape, and the shape matters. At 10% of the speed of light, the factor is about 1.005, which is to say, a half of 1%. At half the speed of light, it is about 1.155. At 90%, it is about 2.29. At 99%, it is about 7.09. At 99.9%, it is about 22.4. And at 99.999%, it is about 224. Notice what that curve does. For almost the entire range of speeds available to anything you will ever encounter, it barely moves. All of the drama is compressed into the last sliver before light speed, where it climbs without any limit at all. This is why the effect feels absent from ordinary life, and then, quite suddenly, feels like the only thing happening. There is a detail about that 1905 paper that I think is worth pausing on. It is titled, in translation, On the Electrodynamics of Moving Bodies. It was received at the end of June and published in September, and it contains no citations at all, not one reference to any other work, which for a physics paper is close to unheard of. And tucked into it, almost in passing, is an explicit prediction of exactly the effect we are discussing. Einstein writes that a clock carried around a closed curve and returned to its starting point will be found to lag behind a clock that stayed put. He wrote that down in 1905. Nobody tested it until 1971. The prediction sat in the literature, uncontested and unverified, for 66 years. It is also worth being precise about what was actually new. Hendrik Lorentz had already written down the transformation equations by 1904, and Henri Poincaré had already named them after him. The mathematics was, in a real sense, sitting there. What neither of them did was insist that the transformed time was the actual time, the time an actual clock actually reads. They treated it as a bookkeeping device, a mathematical convenience that made the equations of electromagnetism come out right, while the real time, the true time, ticked away underneath. Einstein's contribution was to refuse that move. He said the equations were about clocks, and once you say the equations are about clocks, you have committed yourself to everything that follows in this video, whether you like it or not. The second one, the gravitational effect, came from the work that became general relativity in 1915, and it is the one we started with, the reason your head is older than your feet. And here is the thing that took me a long time to appreciate. Those are not two separate phenomena that happen to look similar. They are the same statement made twice. Both of them come out of the geometry of space-time, and in almost every real situation, both are running at once, often in opposite directions, and you have to add them up to find out which way a given clock will drift. But I want to come back to the twins, because there is something buried in that story that I think does real damage, and it does the damage precisely because the story is so satisfying. Listen to how the twin paradox is usually phrased. The traveller comes home younger. They missed some time. They skipped ahead. They lost the years their sibling lived through. Every one of those phrasings contains the same hidden assumption, and it is so natural that it slides past without inspection. Each of them assumes that there was a real amount of time that passed while the ship was away, and that the traveller, through the peculiar mechanics of high-speed flight, somehow failed to receive their share of it. The time was there. They just did not get it. It is framed as a kind of theft, or a discount, or a technicality in the accounting. That framing is a comfort, and it is a comfort because it leaves the important thing untouched. It preserves the idea that underneath all the disagreement between clocks, there is a real duration, an actual, correct, universal amount of elapsed time, and that the various clocks are simply reporting it with different degrees of fidelity. On this picture, time dilation is a measurement problem. Somebody, somewhere, has the right number, and the traveling twins' watch is a slightly unreliable instrument. I am telling you this now, at the very start, so that you can watch for it. Because as we go through the evidence, you will feel the pull of that assumption again and again. Every time two clocks disagree, some part of your mind will want to know which of them is telling the truth. That instinct is going to come up in the muon experiments, in the aeroplane experiments, in the satellite corrections, and it is going to come up in its most extreme form at the edge of a black hole. It is the most natural question in the world, and the answer to it is the reason this topic is far scarier than the twin story suggests. So let me pose the question directly, and then let me refuse to answer it for a while. When two identical, perfectly functioning clocks are synchronized, separated, and brought back together, and they disagree, which one is right? By the end of tonight, you will know exactly what physics says about that question, and you will know why the answer is not a number. But we are not going to get there by argument. We are going to get there by evidence, because the conclusion is only unavoidable once you have seen how many independent ways this has been measured, and how thoroughly every escape route has already been closed. So we begin where the physicists began, not with a spaceship, with a stairwell, a tower at Harvard, and a beam of gamma rays falling 22.5 meters in the dark. Part 3. 2 clocks, 1 bench. The Jefferson Physical Laboratory at Harvard has a tower in it. It is not a landmark. It is a normal piece of a normal university building, about 22.5 meters from the bottom to the top, which is roughly 7 stories, and which is a height that people in that building climbed without thinking about it every working day. In 1959, Robert Pound and his graduate student Glenn Rebka decided to use that stairwell to measure the rate of time. The technique available to them was brand new. A year earlier, a young German physicist named Rudolf Nussbauer had discovered an effect that let certain atomic nuclei emit and absorb gamma rays with almost no recoil, which in turn meant those gamma rays had an astonishingly sharp, precisely defined frequency. It was such a useful discovery that Nussbauer received the Nobel Prize for it in 1961, 3 years after publishing, at the age of 32. That is one of the shortest gaps between a discovery and a Nobel in the history of the subject. Pound and Rebka took an iron-57 source, which emits gamma rays at 14.4 thousand electron volts, and set it at one end of the tower with a detector at the other. Then they asked a simple question. If time runs slower at the bottom of the tower, then a gamma ray emitted at the bottom and traveling upward should arrive at the top with a slightly lower frequency than the atoms up there expect. The nuclei at the top should refuse to absorb it, and that refusal is measurable. The predicted size of the effect over 22.5 meters is about 2.5 parts in 1,000 trillion. To put that in perspective, it is a fractional shift of about 2.5 times 10 to the minus 15, which means that if the gamma ray were a musical note played at concert pitch, the shift would be less than 1/billionth of the width of a single semitone. They measured it. Their result was 2.57 parts in 1,000 trillion, plus or minus 0.26. The prediction was confirmed to within about 10%, and the paper, with the wonderful title Apparent Weight of Photons, appeared in Physical Review Letters on the 1st of April 1960. 4 years later, Pound, working with Joseph Snyder, tightened the agreement to about 1%. There is a small joke buried in that experiment that I find genuinely delightful. Their biggest source of systematic error was the temperature of the iron foil. The nuclei in a warm solid are vibrating, and vibrating nuclei are moving, and moving nuclei experience velocity time dilation, which shifts the emitted frequency. So the experiment designed to measure gravitational time dilation was limited in precision by kinematic time dilation. They had to control the temperature of the source to fractions of a degree, not because the equipment was fussy, but because the very effect they were hunting was hiding inside their own thermometer. That was gravity. 12 years later, somebody put the whole thing on an aeroplane. Picture a departure gate in October of 1971. There are 4 cesium beam atomic clocks in the boarding area, each one a substantial rack of equipment with its own power supply and cabling. And each one has a ticket. Not cargo. Seats. They are strapped into the cabin like passengers, and the flight manifests carry an entry for a passenger named, more or less, Mr. Clock. Joseph Hafele and Richard Keating are travelling with them, watching the racks, monitoring the power, and doing very little else, because the experiment consists of going somewhere and coming back. They fly east, all the way around the world, on scheduled commercial flights. Then they come home, and they fly west, all the way around the world, on scheduled commercial flights. The total cost of the project is on the order of $8,000, and most of that is airfare. It is possibly the cheapest fundamental physics experiment of the 20th century. And then they bring the clocks back to the United States Naval Observatory, where the reference ensemble has been sitting still the entire time, and they set them down side by side on a bench, and they read them. The eastward clocks had lost 59 billionths of a second, give or take 10. The prediction had been a loss of 40 billionths, give or take 23. The westward clocks had gained 273 billionths of a second, give or take 7. The prediction had been a gain of 275, give or take 21. I want to make sure the important detail there does not slide past. It is not that the clocks disagreed, it is that they disagreed in opposite directions, and the direction was predicted in advance. Flying east means flying in the same direction the Earth is rotating, so the aircraft's speed adds to the ground speed and the clock loses time. Flying west means flying against the rotation, so the aircraft's speed subtracts from it and the clock gains. The altitude effect pushes both flights in the positive direction, and when you add the two contributions together with the correct signs, you get a negative number for the eastbound trip and a positive one for the westbound. That sign flip is not something you can produce by a clock drifting or malfunctioning. A drifting clock does not know which way the plane is pointing. And notice what the bench does to the other objection. A person who wants to explain all this away might reasonably say that these effects are illusions of signal delay, that we are simply measuring how long light took to get from one place to another. That explanation cannot survive a bench. The clocks were in the same room, at the same table, at the same moment, being read by the same eyes. There was no signal in flight between them. There was nothing left to correct for. The numbers just did not match, and they never would again. There is a fair criticism of the 1971 experiment that ought to be mentioned, because it matters for how confident we are allowed to be. The individual cesium clocks of that era drifted by amounts comparable to the effect being measured, and Hafele and Keating had to do real statistical work to pull the signal out of 4 instruments that were each wandering. Critics pointed this out at the time, and they were not being unreasonable. The reason nobody argues about it now is that the experiment has been repeated with far better clocks, most notably by the National Physical Laboratory in the mid-1990s and again in 2005, and the modern versions confirm the original comfortably, with margins the 1971 team could only have dreamed of. This is what a healthy result looks like over time. The first version is scrappy and contested, and then the instruments improve, and the number stays exactly where it was. Between those two experiments, the gravitational effect also went to space. In 1976, Robert Vesso, Martin Levine, and their collaborators loaded a hydrogen maser onto a Scout rocket and fired it almost straight up, to an apogee of about 10,000 kilometers. For roughly 2 hours, they compared its frequency against masers on the ground as it climbed out of the gravitational well and fell back into it. The observed shift matched general relativity to about 70 parts in a million. That was an improvement of roughly a factor of 10,000 over Pound and Rebka, achieved in a single suborbital flight, on a vehicle that spent most of the mission simply falling. Which brings us to the sentence I want you to carry through the rest of this video, because we are going to need it later in a much darker context. No clock is wrong. Not the ones on the plane, not the one on the ground, not the source at the bottom of the Harvard Tower, or the absorber at the top. Every single one of these instruments was working exactly as designed, and their disagreement is not a flaw in any of them. And if you think that is a strange thing to say about a piece of laboratory equipment, wait until you hear about the things falling out of the sky above your head, which by every reasonable accounting should not be able to reach you at all. Part 4. The particles that should not be here. Something is falling through you right now, and it has been falling through you your entire life, and by the standard arithmetic of its own existence, it should never have got here. About 15 kilometers above your head, high in the upper atmosphere, protons arriving from somewhere out in the galaxy are slamming into the nuclei of air molecules. Those collisions produce showers of particles, and among the debris are muons. A muon is essentially a heavy electron, same charge, about 207 times the mass. And it is unstable. Left alone, sitting still, a muon survives on average for about 2.197 microseconds before it decays. Now do the arithmetic that anyone would do. 2.197 microseconds multiplied by the speed of light, which is about 300 million meters per second, gives you roughly 660 meters. That is the absolute best case. That is how far a muon could travel if it moved at exactly the speed of light for its entire average lifetime, which nothing with mass can actually do. 660 meters. And they are being created 15 kilometers up. So the expectation is straightforward. Muons should die roughly 23 lifetimes before reaching the ground. Fewer than 1 in 1,000 should survive the trip. The rain should stop long before it arrives. It does not stop. Muons arrive at sea level in enormous numbers. Something on the order of 1 passes through every square centimeter of horizontal surface every minute. Several are passing through your body as you listen to this, without any sensation, and one of them will occasionally break a chemical bond somewhere inside you and move on. Bruno Rossi and David Hall established the shape of this in 1941 by counting muons at altitude and at sea level and comparing the survival rate against the rate a fixed decay clock would predict. But the version that became famous, the one that ended up on film and in undergraduate courses ever since, was done by David Frisch and James Smith in 1963. They took their detector to the summit of Mount Washington in New Hampshire, 1,907 meters up. They counted muons in a narrow band of velocity, right around 99.5% of the speed of light. Then they brought the same apparatus down to Cambridge, Massachusetts, at sea level, and counted again. If the muon's internal clock ran at the same rate as everyone else's, then out of 568 muons counted on the summit, about 27 should have survived the drop to sea level. They measured about 412, not 27, 412, roughly 15 times more survivors than a universal clock permits. There is a way of stating that, which I think is worth sitting with. The muons are not being protected. Nothing is shielding them. From their own point of view, absolutely nothing unusual is happening. They live their 2.2 microseconds, exactly as advertised, and then they decay on schedule. It is the mountain that is short. In the muon's own accounting, that 1,900 meters of New Hampshire granite and air compresses to a couple of 100 meters, and the trip is easy. Both descriptions are complete. Neither is a correction to the other. Now, a stubborn person could still push back here. They could say that these particles are being hurled through the atmosphere at ferocious speeds, colliding, being buffeted, and that whatever internal mechanism governs their decay is simply being disturbed by all that violence. It is not time that changed, it is the particle that got knocked about. That objection was closed, thoroughly, by an experiment at CERN in the 1970s. They built a muon storage ring, a machine that takes muons and holds them circulating in a magnetic field so you can watch them decay at leisure. The muons in that ring were moving fast enough to give a Lorentz factor of 29.33. Their measured lifetimes in the laboratory came out to 64.419 microseconds for positive muons, plus or minus 58 thousandths, and 64.368 for negative ones, against a proper lifetime of 2.1948 microseconds. The dilation factor agreed with special relativity to within about 2 parts in 1,000, and the final report from the collaboration tightened that to something like 8 parts in 10,000. But here is the number that closes the argument. To hold a particle moving that fast on a circular path, you have to bend it hard. The transverse acceleration those muons were subjected to is on the order of 10 to the 18 times the acceleration you feel standing on the Earth. A billion g. And it made no difference whatsoever. The dilation depended only on the speed. There was no extra term for the acceleration, no correction for the violence, nothing. A muon being wrenched around a magnet at a billion Ga decayed at exactly the same dilated rate as a muon flying in a perfectly straight line at the same velocity. Whatever is happening here, it is not being done to the clock. And this is not an isolated laboratory curiosity either. Every particle accelerator running on Earth today is, among other things, a time dilation machine, and the effect is treated as ordinary engineering. At the Large Hadron Collider, protons at 6.8 trillion electron volts have a Lorentz factor of around 7,250. Beam lifetimes, collimation design, the length of the decay channels built for unstable particles. All of it is calculated, assuming that the particle's own clocks are running slow by exactly the predicted factor. If the assumption were wrong, the machines would not work, and the mismatch would show up within hours of switching them on. The same is true further afield. The entire study of atmospheric neutrinos, the field that eventually revealed that neutrinos have mass and change flavor in flight, which is one of the most important discoveries in particle physics of the last 30 years, rests on modeling pion and muon decay chains in the upper atmosphere. Time dilation is the dominant term in those models. It is not a hypothesis being tested. It is the ruler. Nothing is squeezing the muon. Nothing is interfering with its decay mechanism. Nothing is applying a force to the cesium in the aeroplane or the iron in the Harvard Tower. The instruments are not being affected. Something else is going on, and it is not a property of the instruments at all. Which raises an uncomfortable possibility. If nothing is being done to the clocks, then perhaps we should stop looking at the clocks. And if we do that, we are going to need to look somewhere much smaller and much more precise before we can say what we are actually measuring. Part 5. Down to the millimetre. Everything we have looked at so far involved either a mountain, an aeroplane, or a particle moving at nearly the speed of light. That is convenient, in a way, because it keeps the effect at arm's length. It happens out there, to things doing something unusual. The last 20 years took that comfort away, and the way it happened is worth understanding, because it comes down to a single change in how we build clocks. A cesium clock, the kind that has defined the second since 1967, works by counting oscillations in a microwave transition at 9,192,631,770 cycles per second. That is a lot of ticks. But an optical clock counts oscillations of visible light, and visible light oscillates roughly 100,000 times faster. Strontium's clock transition sits at about 429 trillion cycles per second. The aluminium ion transition used at Boulder is at about 1,121 trillion. The logic is the same as the difference between a ruler marked in centimeters and a ruler marked in microns. A faster oscillator divides time more finely, and finer division means you can see smaller differences. In 2010, a group at the National Institute of Standards and Technology in Boulder, Chi-Wei Cho, David Hume, Till Rosenband, and David Wineland, published a paper in Science with the almost defiantly plain title, Optical Clocks and Relativity. They had 2 aluminium-ion clocks, and they did 2 things with them. First, they raised one of the clocks by 33 centimeters. 33 centimeters, about the height of a stack of books. The difference between the surface of a desk and the seat of the chair pulled up to it. A distance you can span with one hand and a bit of forearm. And the elevated clock ran fast, by a fraction of about 4 parts in 100 quadrillion, exactly as the equations required. Then they took one of the ions and set it moving at about 10 meters per second. 10 meters per second is roughly the top speed of a very fast human sprinter. It is not a relativistic velocity by any stretch of the imagination, and the moving clock lost time, measurably, by the amount special relativity says it should. That was the moment the effect stopped being astronomical. Both of Einstein's predictions, the one from 1905 about motion and the one from 1907 about gravity, were demonstrated across a distance you can reach and at a speed a person can run. 12 years later, the scale collapsed again. In February of 2022, a team based at Gila and NIST in Boulder published a result in Nature with the title Resolving the Gravitational Redshift Across a Millimeter Scale Atomic Sample. Not 2 clocks in 2 labs, not 2 clocks on 2 tables, 1 sample. Let me take you inside it. You are looking at a cloud of strontium atoms, cooled to within a hair of absolute zero, held in place by intersecting laser beams. The trap is arranged vertically, so the atoms are stacked in a column of thin, flat layers, like a very short pile of pancakes made of light. The whole column is 1 millimeter tall. If you set it on your fingertip, it would be about the thickness of your fingernail. Now shrink down and stand inside it. Look at the layer above you. Those atoms are running fast. Look at the layer below you. Those atoms are running slow. There is no motion here. Nothing is traveling. Nothing is accelerating. There is no rocket, no aeroplane, no cosmic ray, no black hole. There is a millimeter of height on a laboratory table in Colorado, and across that millimeter, from the bottom of the cloud to the top, time is running at 2 different rates, and the difference is not a calculation. It is sitting in the data, resolved, with a fractional measurement uncertainty of about 7.6 parts in 10 sextillion. Come back out. There is a detail in how that measurement works that makes it stranger rather than less strange. The atoms in that column are all identical. They are the same isotope, prepared the same way, held in the same trap, addressed by the same laser. There is no difference between the atom at the top and the atom at the bottom, except its position in the field of the Earth. And that positional difference, 1 millimeter closer to a planet, is enough to make them physically distinguishable, because they no longer agree about the frequency of the light that excites them. 2 atoms that are the same in every intrinsic respect have become different objects by virtue of where they are sitting. 2 years after that, in July of 2024, another Gila group, Alexander Apley, Kyung-tae Kim, William Warfield, Mariana Safronova, and Jun Ye, pushed a strontium lattice clock to a total systematic uncertainty of 8.1 parts in 10 quintillion. It was better than a factor of 2 improvement on the previous best clock in the world. and it set the accuracy benchmark for every optical clock built to that point. At that level of accuracy, the clock is sensitive to a change in its own elevation of about 1 centimetre. 1 centimetre is the width of a fingertip. It is less than the thickness of a hardback book, less than the depth of the lip on a laboratory bench, less than the distance a table settles into a carpet over a winter. An instrument that's stable, left running from the birth of the solar system until the present day, would have drifted by around 1/10 of a second across 4.5 billion years. That is the sensitivity we are pointing at, a fingertip's worth of height. Think about what that sentence means in practice. If you were to pick up that instrument and set it down on a slightly thicker book, it would notice. Not in principle. In the data, on the day, the physical height of a clock above the floor is now a routine systematic that has to be measured and subtracted before you can extract any other physics from it. Altitude has become a correction term in the operational definition of the second. The consequences have already started running in the other direction. If a clock can sense 1 centimetre of elevation, then a network of such clocks is a gravity mapping instrument. The technique has a name, chronometric leveling, and it is now an active field in geodesy. You place clocks at various points on the Earth's surface, compare their rates, and read out the shape of the planet's gravitational field directly, without a single measurement of distance or mass. The clocks are no longer being used to measure time. Time is being used to measure the Earth. And because optical clocks have now overtaken the cesium standard by such a margin, the definition of the second itself is under review, with a redefinition being targeted for somewhere around the end of this decade. The unit will be rebuilt around instruments precise enough that where you put them changes what they say. There is a pattern here that this channel keeps running into, and it is worth naming in passing. Every time we build an instrument precise enough to see a gravitational effect clearly, the effect turns out to be exactly where the theory said it would be, and the theory turns out to explain slightly less than we hoped. Precision keeps confirming general relativity, and keeps failing to tell us what general relativity is describing. The clocks are a particularly clean case of that. They have confirmed the prediction across 15 orders of magnitude, and they have brought us no closer at all to knowing what the quantity being measured actually is. So here is where the evidence has arrived. We started with a tower and moved to an aeroplane, and then to particles raining out of the sky, and then to a stack of books, and then to a millimetre, and then to a centimetre. At every step, the effect was there, and at every step, it was exactly the predicted size. There is no scale at which it vanishes. There is only the scale at which your instrument gives up. And through all of it, the question we posed at the beginning has been quietly waiting, getting harder to avoid with every experiment. If the clock at the top of the tower and the clock at the bottom of the tower disagree, and neither of them is broken, then which one is telling you how much time has actually passed? Part 6. Step back for a moment. Let us stop and put the pieces on the table together, because we have covered a lot of ground, and the shape of it matters more than any individual result. We have looked at cesium beam clocks, which work by counting microwave transitions in a beam of hot atoms. We have looked at hydrogen masers, which work by stimulated emission in a resonant cavity. We have looked at trapped aluminium ions, held motionless in electromagnetic fields and interrogated by ultraviolet lasers. We have looked at strontium atoms suspended in optical lattices at temperatures a fraction above absolute zero. We have looked at iron 57 nuclei emitting gamma rays. We have looked at muons, which are not clocks at all in any designed sense. They are unstable particles whose decay happens to be probabilistic and steady. We have looked at satellites in orbit and at aeroplanes on scheduled commercial routes. These things have almost nothing in common. They are built on different physics, at different energies, by different people, in different decades, using different assumptions. There is no shared component that could be failing in the same way across all of them. A design flaw in a cesium beam tube tells you nothing about the decay of a muon, and every single one of them disagrees with every other one by precisely the amounts that geometry predicts, and not one of them is malfunctioning. That is the situation. And the situation demands an obvious question, which is the one we posed at the start and have been putting off ever since. Which of them is right? I want to be very careful here, because the answer I am about to give sounds like an evasion, and it is not one. The question has no answer, and it has no answer not because we lack the information, and not because the experiment is too difficult, and not because there is some subtlety we have yet to work out. It has no answer because the question is asking for something that the physics does not contain. Let me show you what I mean by taking the simplest case and turning it around. In special relativity, the velocity effect is completely reciprocal. If a ship passes you at half the speed of light, you will observe its clocks running slow. But the crew of that ship will observe your clocks running slow by exactly the same factor. Both of you are correct. There is no experiment either of you can perform. None, not one, no matter how clever or how well funded, that establishes which of you is really moving and which is really at rest. The reason is not that the experiment is hard. It is that there is no fact of the matter to detect. Now, the natural response to that is that it sounds like a contradiction. You cannot both be slower than the other. Surely one of you must be wrong. And this is where the resolution comes in, and it is precise. The two of you are not comparing clocks. You are each comparing your own clock against your own idea of what is happening simultaneously, far away, on the other person's ship. And simultaneity, across a distance, is exactly the thing relativity does not give you. You each have a perfectly consistent way of slicing up the universe into moments, and your slices are tilted relative to each other, and neither slicing is the correct one. The contradiction only threatens to become real when the two of you meet, because then the comparison happens at a single place, at a single event, with both dials visible at once, and there is nothing left to interpret. And what happens at that point is that the readings differ, and everybody in the universe agrees about the readings, and nobody is contradicted by anybody. There is a long and slightly sad history attached to people refusing that resolution. The most prominent example is Herbert Dingle, a genuinely respected British physicist who had been president of the Royal Astronomical Society and who spent roughly the last 2 decades of his life arguing in print that the twin paradox proved special relativity was internally contradictory. His book on the subject came out in 1972. His error is instructive precisely because it is the same one almost everyone makes on first contact. He took the reciprocal symmetry, which applies while the two observers are apart and comparing distant simultaneities, and applied it to the reunion, where they are not comparing distant simultaneities at all. The symmetry is real. It just does not extend to the moment when the two dials are side by side. That is what Hafele and Keating did with a bench. That is what the strontium clock does within a millimetre. The disagreement is real, it survives comparison, and it does not resolve into one true number. And I want you to sit with what that means for you personally, because it is not abstract. You have already aged differently from everyone you know. Every flight you have ever taken put you on a different road from the people who stayed on the ground. Every year you spent living at a different altitude from a sibling put a gap between you. Every hour you have spent standing rather than lying down has widened the gradient inside your own body. You cannot feel any of it. It is measured in billionths of a second at most. But it is not an approximation, and it is not a rounding error. And here is the part I keep coming back to. There is no procedure for fixing it. Nowhere in physics is there an operation that puts two people back onto the same clock. There is no resynchronization. You cannot catch up, and you cannot be caught up with. Whatever difference has accumulated between you and the person sitting next to you is now a permanent feature of the universe, and it will still be a feature of the universe after both of you are gone. It is worth noticing how thoroughly the escape routes have been closed, one at a time, by the experiments we have walked through. The idea that the clocks are simply breaking under stress died in the CERN storage ring, where a billion gains of acceleration produce no extra term at all. The idea that it is an artifact of signal delay died on a bench at the Naval Observatory, where two clocks in the same room disagreed with nothing travelling between them. The idea that it is peculiar to one technology died the moment 6 unrelated technologies gave the same answer. The idea that it requires extreme conditions died at 33 centimeters, and then again at 1 millimetre, and then again at 1 centimetre. Each of those was a reasonable objection when it was raised. Each of them was tested. Each of them failed. What is left is not a theory that has survived scrutiny by being vague. It is a theory that keeps making sharp, checkable, unwelcome predictions, and keeps being right. Currently, that difference is nanoseconds. That is a fact about human beings and how slowly we move, not a fact about the physics. The physics contains no threshold beneath which the statement stops applying. It simply keeps being true, all the way down, and, as we are about to see, all the way up. So we still have the question in front of us. Two clocks disagree. Neither is broken. Which one measured how much time actually passed? The answer exists. It is not a number, and it is not a dodge, and it has been sitting quietly in the mathematics since 1908, when a mathematician stood up in Cologne and told a room full of physicists that space and time were finished as separate ideas. Once you see it, the whole thing rearranges. And it rearranges in a direction that I do not think most people expect. Part 7. A route, not a rate. Two cars leave the same town on the same morning and arrive at the same second town that evening. When they park, the drivers compare odometers and the numbers do not match. One reads 200 kilometers, the other reads 340. Nobody finds this alarming. Nobody asks which odometer is correct, or how far the two towns really are apart, or which driver was cheated out of the distance they should have travelled. Everyone understands immediately what happened. The cars took different roads. An odometer does not measure the separation between two towns. It measures the length of the road the car actually drove. Two roads between the same pair of towns can have any lengths you like, and both readings are exactly right. That is what a clock is. A clock does not measure how much time has passed. A clock measures the length of the path it took through space-time, and nothing else. When you synchronize two clocks, separate them, and bring them back together, you have sent them along two different roads between the same 2 points, and their readings differ. For exactly the same reason, the odometers differ, not because one of them ran badly, or because they went different ways. This is the answer. Elapsed time is a property of a route, not a property of the universe. It is not a rate at which something universal is being consumed. It is a length. A route, not a rate. Hold on to that phrasing, because it is going to do a great deal of work before the end of tonight. Hermann Minkowski is the one who made this visible. In a lecture in Cologne in 1908, he told the audience that space by itself and time by itself were destined to fade into shadows, and that only a union of the two would preserve any independent reality. Einstein initially found the geometric reformulation irritating. He described it, more or less, as superfluous learnedness, and then a few years later built general relativity entirely on top of it, because it turned out to be the only language in which the theory could be written. What Minkowski gave us was a way to measure the length of a path through space-time, and it looks almost exactly like the Pythagorean theorem you learned in school, with one change. In ordinary geometry, you find a distance by squaring the components and adding them up. In space-time, You square the components, and you subtract the spatial part from the temporal part. 1 minus sign. That is the entire difference between the geometry of a tabletop and the geometry of the universe. And that 1 minus sign turns the whole intuition inside out. In ordinary geometry, a straight line is the shortest distance between 2 points. Any detour makes the journey longer. In space-time, because of the minus sign, it goes the other way. Between two events, the straight world line, the one that just sits there, unaccelerated, not going anywhere, is the path of the greatest elapsed time. Every deviation from it is shorter. Every detour costs you. Read that again slowly, because it is one of the strangest sentences in physics, and it is almost never said out loud. Moving is a way of getting less time, not less time relative to something else, in some bookkeeping sense, less time on your own watch, less biological aging, fewer heartbeats between departure and return, and doing nothing at all, drifting, falling freely, exerting no effort, and feeling no force, is the way to get the most. This has a formal name in general relativity. It is called the principle of extremal aging, and it is powerful enough that you can derive gravity from it. You do not need a force. You need only the rule that unforced bodies follow the path that maximizes their own elapsed time, and the orbits of the planets fall out of it. The Earth is not being pulled around the Sun. The Earth is taking the route through space-time that gives it the longest possible life, and that route happens to be an ellipse. Which means that when you stand up, when you brace against the floor, when you push back against the ground so as not to fall, you are steering off the path of maximum aging. The floor is what stops you following the longest route. Every engine burn, every acceleration, every act of resistance to gravity is a subtraction from your own total. Falling is free, standing costs. I find that inversion genuinely difficult to hold in my head, and I think the reason is that it runs against a very old moral intuition, that effort is how you get more of things, and that stillness is how you lose. Here the arithmetic runs the other way. The thing that gives you the most time is doing absolutely nothing, and every push you make against the universe is deducted from your own account. Not metaphorically, in seconds. Once you have that rule in your hands, a whole set of scattered facts collapses into one statement. A satellite in a high orbit ages faster than you do. A person living on a mountain ages faster than a person living in the valley below them. A person who spends their life running marathons ages very slightly less than a person who spends it in an armchair, by nanoseconds, but really. Your head ages faster than your feet. The muons survive the fall. The cesium clock loses time flying east and gains it flying west. Every one of those is the same sentence. There is not a gravitational effect and a separate motion effect that happen to resemble each other. There is one rule about the lengths of roads, and these are different roads. And there is a limiting case at the far end of it, which this channel has looked at before, and which I will only name in passing here. If you push a route all the way to the speed of light, the length of that route goes to 0. Light does not take a short trip. It takes no trip at all, in the only sense of duration that means anything. The straight route is the longest, the bent routes are shorter, and the null route, the one light takes, is the shortest possible, which is none. Now go back to the twins with this in hand, and watch the paradox evaporate. One twin stays home and takes the straight road. The other twin accelerates away, coasts, decelerates, turns, and comes back. A bent road. When they meet, the bent road is shorter, so the traveller has less time on them. That is all. There is no paradox to resolve, because there was never a contradiction, only two roads. And notice what this does to the usual explanation. You will often hear that the traveller aged less because they accelerated, as though the acceleration did something to their body or their watch. That is not what happened. The acceleration was only the mechanism that let their road bend. The bending is what cost them the time. The The proof of that is sitting in the Chern storage ring, muons wrenched around at a billion gone, with no acceleration-dependent term anywhere in their decay rate. The force did nothing. The path did everything. Now, I want to correct something at this point, because it is the single most common misreading of relativity, and it gets in the way of everything that follows. People come out of this idea saying that time is subjective, that it is all relative, that your reality is yours, and mine is mine, and nobody can say what is real. That is close to the opposite of what the theory says. Relativity is a theory of invariance. Its entire structure is built around quantities that everybody agrees on, and the elapsed time along a world line is one of them. If you take any path through space-time and hand it to 1,000 different observers moving in 1,000 different ways, every one of them will calculate the same elapsed time for that path. They will disagree, wildly, about how to divide that path into space and time. They will disagree about which events were simultaneous. But they will all compute the same reading on the watch. Your watch reading is not subjective. It is one of the most objective quantities in physics. There is a useful way to see why both of those things can be true at once. Imagine a road drawn across a map. Everyone looking at that map agrees on how long the road is. You could measure it with a piece of string, and everyone would get the same answer. But two people using different coordinate grids, one aligned north-south and one rotated by 40 degrees, will completely disagree about how much of that road runs east and how much runs north. The disagreement is about the grid. The string length is not up for debate. Space-time works the same way, with the one difference we already noted about the minus sign. What is frame-dependent is the grid. How you carve the world into space and into time, which events you call simultaneous, how you label the axes. What is frame-independent is the string length of any world line you care to draw. Different observers use different grids. They all read the same watch. So the strangeness is not that things are vague. Nothing here is vague. The strangeness is much more specific and much more surgical than that. Relativity leaves almost everything intact and removes exactly one item. Look at what survives. Causal order survives absolutely. If A can influence B, then every observer in the universe agrees that A came first, and no frame anywhere ever sees an effect precede its cause. Meetings survive absolutely. When two world lines intersect and two dials are read side by side, that reading is a single fact shared by everyone. The theory is deterministic. It is local. There is no probability in it, and no fuzziness. What does not survive is a single quantity, the total amount of time between two events, considered independently of any route. That quantity does not exist, not as an unknown, not as something too small or too far away to measure. It is not the sort of thing the universe has. Everything else in this video is the working out of that removal, at larger and larger scales, until it stops being an interesting fact about geometry and starts being something considerably harder to sit with. And the first place to look is not a black hole, and it is not the edge of the universe. It is the device in your pocket, where somebody already accepted all of this and quietly built it into the hardware. Part 8. Built into the crystal. There are around 30 satellites in the Global Positioning System constellation, orbiting at an altitude of about 20,200 kilometers, moving at roughly 3.87 kilometers per second. Each one carries atomic clocks, and the entire system works by comparing the arrival times of signals from several satellites at once. Position is derived from timing. That is the whole trick. If the timing is wrong, the position is wrong, and the error is not small, because the signals travel at the speed of light, and a billionth of a second of timing error is 30 centimeters of position error. So consider what the two effects do to those clocks. The satellites are high up, well out of the deepest part of Earth's gravitational well. which means their clocks run fast. That contribution comes to about plus 45 microseconds per day. The satellites are also moving quickly relative to the ground, which means their clocks run slow. That contribution comes to about minus 7 microseconds per day. Add them together, with signs, and you get a net gain of about 38 microseconds every day. Uncorrected, that timing drift produces a position error that grows by roughly 10 kilometers per day. Within about 2 minutes of switching the system on, the error already exceeds the accuracy the system is supposed to deliver. By the end of a week, the receiver in your car would be placing you in a different county. Here is the part I find most telling. The correction is not a software patch. It is not applied on the ground by clever post-processing. And it is not something engineers discovered after launch when the numbers came out strange. The onboard cesium and rubidium standards are deliberately manufactured to run at the wrong frequency. Instead of the nominal 10.23 MHz, they are built to oscillate at about 10.22999999543 MHz, a little slow, on purpose, by exactly the amount required, so that once the satellite is in orbit and the geometry has taken its cut, the clock ticks correctly as seen from the ground. The relativity is compensated in the crystal, in a factory, before the vehicle ever leaves the planet. And it was not a leap of faith either. The earliest satellites in the program, the Block 1 generation, carried a switch that allowed the relativistic frequency offset to be disabled, precisely because there was still institutional nervousness about whether the correction would be needed at the predicted size. The switch was there, so the effect could be verified operationally, in orbit, with the system running. It was switched on. It has been on ever since. Take a moment with the ordinariness of that. Several billion devices are currently in the hands of people who have never thought about any of this, and every one of them is running on the assumption that time does not pass at the same rate in two places. Not as a philosophical position, as a manufacturing specification. Somebody had to put a number on the disagreement, sign off on it, and grind an oscillator to match. The same arithmetic produces a curiosity that I like a great deal. Because the two effects have opposite signs and different dependencies on altitude, there is a specific height at which they cancel exactly. It sits at about 3,180 kilometers above the surface. Below that line, an orbiting clock runs slow overall. Above it, fast. And at that one altitude, a satellite clock keeps perfect ground time, without any correction at all. A thin shell around the Earth, where the two halves of relativity agree to leave each other alone. There is a second cancellation that is even neater. You might expect a clock at the equator to disagree with a clock at the North Pole, since the equator is spinning at about 465 meters per second, and the pole is not. It does not. The equator is also further from the center of the Earth, because the planet bulges, and the gravitational gain almost exactly offsets the velocity loss. That is not a coincidence. Sea level is by definition a surface where the combined potential is constant. Clocks at sea level, anywhere in the world, tick at the same rate, no matter the latitude. And this is the point I want to leave you with, before we turn the dial up. Everything we have been discussing, the missing universal duration, the route instead of the rate, has already been accepted by engineers, priced into hardware, and shipped. It is not a live controversy. It is a line item. The strange thing about your phone is not that it can find you. It is that it can only find you because somebody agreed, in a specification document, that there is no such thing as the correct amount of time. So far, all of this has been tiny, microseconds, nanoseconds, parts in a quadrillion. Now let us stop being polite about it, and see what the same equation does when you point it at something that is genuinely heavy. Part 9. The gradient goes vertical. The equation we have been using does not have a switch on it. There is no clause that says the effect stays small. the factor governing how much a static clock slows down in a gravitational field, is a very simple expression. It is the square root of 1 minus the ratio of two lengths. One of those lengths is how far you are from the center of the object. The other is a length characteristic of the object's mass, called the Schwarzschild radius. For the Earth, that characteristic length is about 9 millimeters. The whole planet's mass, expressed in that particular way, comes out to the size of a marble. That is why every effect we have discussed so far has been measured in nanoseconds and parts per quadrillion. We live very, very far away from our own marble. So let us start walking toward heavier things. The surface of the Sun has a gravitational slowing of about 2 parts in a million. A clock sitting on the solar surface, if such a thing could exist, would fall behind a clock far out in empty space by roughly 66 seconds every year. That is the first point on this ladder, where the effect stops needing laboratory instruments and starts being something you could notice on a wristwatch across a career. Now go to a white dwarf. Sirius B has about the mass of the Sun packed into a body the size of the Earth, and its surface slowing is around 3 parts in 10,000, over 100 times larger than the Sun's. This one is not hypothetical. The gravitational redshift of Sirius B was measured spectroscopically in the early 20th century, and it was one of the first independent confirmations that general relativity was describing something real. Then go to a neutron star. Take about 1.4 times the mass of the Sun and compress it into a sphere roughly 12 kilometers across, a city made of nuclear matter weighing more than a star. Its characteristic length is about 4.13 kilometers. The surface sits at 12. Run the numbers, and the slowing factor comes out at about 0.81. That is a 19% effect, not parts per million, 19%. A clock on that surface runs at roughly 4/5 the rate of the rest of the universe. Somebody standing there, and I recognize the absurdity, since anything arriving at that surface would be spread across it as a film of nuclear matter a few atoms thick, would age at 4/5 of everyone else's rate, permanently. Over a human lifetime, that is a difference of 15 years. The neutron stars are also where this stops being a thought experiment and becomes a working tool. Some neutron stars spin hundreds of times a second and emit beams that sweep past us with extraordinary regularity, millisecond pulsars, some of which are stable to parts in 1,000 trillion over years, which puts them in the same league as the best clocks on Earth. To use them, astronomers have to convert the arrival time of every pulse from the observatory's own frame into a common reference at the center of mass of the solar system, and that conversion includes corrections for the Earth's motion, the Earth's altitude, the Sun's gravitational potential, Jupiter's gravitational potential, and the delay the signal picks up passing through the Sun's own well. That machinery is what made one of the great measurements of the last 50 years possible. The Hulse-Taylor binary pulsar, discovered in 1974, is a pair of neutron stars orbiting each other, and its orbital period is shrinking by about 76.5 microseconds every year as the system radiates gravitational waves away. That was the first evidence gravitational waves exist at all, decades before anyone detected one directly, and it exists only because relativistic timing corrections are handled at the level of nanoseconds as a matter of routine. Keep going. Sagittarius A star, the black hole at the center of our own galaxy, has a mass of about 4.3 million suns. Its characteristic length is about 12.7 million kilometers, a little under 1/10 of the distance from the Earth to the Sun. We have watched a star swing past it. S2 is on a 16-year orbit around Sagittarius A star, and it is a highly stretched ellipse. At its closest approach, it comes within about 120 astronomical units of the whole, which is about 1,400 times that characteristic length, and at that moment, It is moving at about 7,650 kilometers per second. That is 2.5% of the speed of light. A star, moving at 2.5% of light speed. In May of 2018, S2 made that pass, and the gravity collaboration, using the 4 telescopes of the Very Large Telescope in Chile, working together as one instrument, measured the combined gravitational and motional shift in its light. The effect came out at about 200 kilometers per second's worth of redshift, exactly as predicted. 26 years of patient tracking for one pass. And then there are the very large ones. M87 star, the black hole at the center of the galaxy M87, and the first ever to be imaged directly, carries about 6.5 billion solar masses. Its characteristic length is around 128 astronomical units. That is bigger than the orbit of Pluto. You could drop the entire solar system inside that boundary and have room left over. There is a place worth stopping on the way down. At 1.5 times the characteristic length, there is a radius where light itself can orbit, the photon sphere. The slowing factor there is about 0.577, so a clock hovering at that altitude runs at a bit over half the universal rate. And because light circles at that radius, an observer hovering there and looking straight ahead would see the back of their own head, carried all the way around and returned to them. If the hole is spinning, it gets stranger still. A rotating black hole drags space-time around with it, and outside the horizon there is a region, the ergosphere, where that dragging is so complete that nothing can remain still, not slowed, not difficult, impossible. There is no amount of thrust, no engine, no fuel that lets you hover in the ergosphere, because staying in one place would require moving faster than light relative to the local geometry. Everything inside it is carried around whether it likes it or not. That region is not merely a hazard, incidentally. Roger Penrose showed in the 1960s that you can extract energy from it, send an object in, have it split, let one fragment fall onto the hole along a carefully chosen path, and the other fragment comes back out, carrying more energy than the original had going in. The excess is taken from the hole's rotation. For a maximally spinning black hole, up to about 29% of its total mass energy is in principle available this way. The same twisting of local time that makes hovering impossible is what makes the extraction possible. Now let me bring this back to something human, because there is a version of all this that sounds like a gift. Suppose you build a ship that can accelerate at a comfortable 1g indefinitely, enough to give the crew normal weight, pointed forward for the first half of the journey and backward for the second half, so you arrive at rest. Work out the ship time for various destinations, and the numbers are remarkable. Alpha Centauri, 4.37 light-years away, takes about 3.5 years of ship time. The center of our galaxy, 27,000 light-years away, takes about 12 years of ship time. Andromeda, 2.5 million light-years away, takes about 24 years of ship time. And in roughly 45 years of ship time, you could cross the entire currently observable universe. 45 years, a working life, the whole visible universe. I should add the caveat, since it matters, dark energy is pulling the far universe away faster than that, so a great deal of what you could see at departure would be beyond reach by the time you arrived. But the ship time arithmetic is correct, and it is correct for the same reason everything else in this video is correct. The crew are not going fast in some sense that shortens the trip for them. They are taking a different road, and their road is shorter. That is the version of this that gets people excited, and I understand why. But look at what is on the other side of the ledger. That 12-year trip to the galactic center takes 27,000 years back home. The 24-year trip to Andromeda takes 2.5 million. And here is the thing I want you to notice, because it is the entire argument of this video in one example. There is no third number. 12 years is not the crew's subjective experience of a journey that objectively took 27,000. 27,000 is not the real duration that the crew somehow cheated. Both numbers are the length of a road. Both are final. Both are true. The question, how long did that trip actually take, does not have an answer, because it is asking for a duration that belongs to no root. We have now watched the slowing factor go from parts in a quadrillion to 2 parts in a million to 19% to a little over a half. There is only one place left for it to go. Part 10. 2 complete accounts of one death. Let us walk the last part of the ladder down. At twice the characteristic length from the center of a non-rotating black hole, a clock, hovering in place, runs at about 0.707 of the rate far away. Call it 70%. At 1.5 times, at the photon sphere, it is 0.577, a little over half. At 1.1 times, it is 0.3, just under a third. At 1.01 times, it is 0.0995, 10%. At 1.0001 times, it is 0.01, 1%. And at exactly the characteristic length, at the event horizon itself, it is 0. I want to be precise about that word, because the ladder makes it look like the end of a sequence, and it is not. It is not a very small number. It is not 1 over an enormous number. It is not a rate so slow that it would take longer than the age of the universe to tick once. It is 0. There is no ratio between a clock at the horizon and a clock far away, in the same way that there is no ratio between any number and nothing at all. The relationship does not become extreme. It stops existing. There is something worth noting about that ladder before we leave it, which is what it costs to sit on any rung of it. Those numbers are for a clock hovering, held stationary against the pull. That is not a passive state. To hover just outside a horizon requires an enormous, continuous, ferocious thrust. And the closer you get, the more absurd the requirement becomes, rising without limit as you approach the boundary. So the ladder is not a set of places you can visit. It is a set of prices, and the last one is infinite. Now let us send someone in. You are in a ship approaching M87 star. It is the largest black hole anyone has photographed, 6.5 billion times the mass of the Sun, and its horizon is bigger than the orbit of Pluto. You have decided to go in. The first thing to understand is that nothing happens. There is no wall, there is no membrane, no shimmer, no boundary layer, no barrier of light. If you were expecting the horizon to look like something, it does not, and it cannot. Because the horizon is not a place. It is a statement about which routes can still get back out. You could pass through it with your eyes open and see nothing at all. The second thing is that it will not hurt. For a hole this large, the difference in gravitational pull between your head and your feet at the moment of crossing is gentler than the tidal stretching you feel standing on the surface of the Earth right now. The stretching that shreds objects near small black holes scales inversely with the square of the mass, and this thing is 6.5 billion solar masses. You cross intact. You cross comfortably. You cross without any local evidence that anything has occurred. The third thing is that your watch keeps working. It ticks at exactly 1 second per second, because that is what a watch does. Always, everywhere, without exception. A watch measures the length of your road, and you are on your road. Nothing about you is running slowly. You breathe normally. Your heart beats at its usual rate. You look at your hands, and they are your hands. And you now have a definite, calculable amount of life left, and it is not long. For a whole of this mass, the maximum proper time from horizon to the center is about 5.5 hours. 5.5 hours, on your own watch, from the crossing to the end. It is a finite, definite, ordinary number. You could set a timer. For Sagittarius A star, it would be about 21 seconds. For a black hole of 10 solar masses, it would be about 10 microseconds. And there is a detail in that arithmetic which is almost cruel. The 5.5 hours is the maximum. It is the longest you can possibly last, and you get it by doing nothing, by falling freely, straight in, without using the engines at all. If you fire the thrusters to slow your descent, if you fight it, if you do the thing every instinct in a human body says to do when falling, you shorten the time you have left. Resisting costs you. It is the same rule we met when we were talking about standing up versus lying down. Arriving here, in its most brutal possible form, the path of maximum aging is the path of doing absolutely nothing, and inside a horizon, that is the only mercy available. While that is happening, you can look back the way you came. The outside universe is still visible. The horizon does not close over you like a lid, and the light from it arrives compressed into a shrinking window of sky. Contrary to a common description, you do not see the entire future of the universe play out in fast forward. You see a bright, distorted, blue-shifted patch of everything behind you, and you have 5.5 hours to look at it. So there is a fact here, and it is a hard one. From the inside, there is a moment at which you die, and it is a specific moment on a specific watch, and it arrives on schedule. Now go outside. You are on a station far away, and you have been watching your colleague's ship all the way down with the best instruments ever built. What do you see? You see the ship slow. You see it approach the horizon and never quite arrive. The light coming from it shifts steadily redder, then into the infrared, then into the microwave, then into wavelengths there is no name for. It dims, and dims, and dims. The interval between the photons you receive stretches without bound. In the mathematics, the ship never crosses, not slowly, never. Your description of the universe, a complete, valid, self-consistent description with nothing missing from it, contains no event corresponding to your colleague passing through the horizon. You can wait for as long as you like. You can wait until the stars burn out. There is no moment in your account at which it happens. And yet, in practice, you do not get to watch a frozen image hanging there forever, because the dimming is exponential. The characteristic timescale for the fade is the crossing time of the hole itself. For M87 star, that is around 36 hours. For Sagittarius A star, it is about 42 seconds. And for a stellar mass hole, it is about 10 microseconds. Within a few multiples of that, the number of photons still reaching you drops below 1. The image does not linger. It reddens, dims, and is simply gone, while formerly never having arrived. So here are the two accounts, side by side. Account 1. Your colleague crossed the horizon at a specific moment, felt nothing, and died 5.5 hours later. Account 2. Your colleague never crossed the horizon, and there is no moment in the history of the universe at which they did. Both accounts are complete. Neither is missing information. Neither is an approximation of the other. There is no observation, none, from any vantage point, with any instrument, given any amount of patience, that can settle which of them describes what really happened, because both of them describe what really happened. No clock is wrong. I said that in the third part of this video, and I said it then, as a reassurance. Nothing malfunctioned in the aeroplanes. Nothing malfunctioned in the tower. It was a statement about the quality of our instruments, and it was meant to be comforting. Here, it means something else entirely. Here, no clock is wrong, because there is nothing for a clock to be wrong about. The reason your colleague's watch and your station's clocks cannot be reconciled is not that one of them lost track. It is that the question they are being asked to answer, has this person died yet, is not a question about the universe. It is a question that assumes a shared present moment in which the answer is either yes or no, and there is no such moment to consult. Sit with that for a second, because I think it is the hardest thing in this whole subject. Somewhere out there, in principle, right now, there is a person for whom the question, are they dead, is not unanswered. It is unanswerable. Not because the information is hidden behind a horizon, though it is, not because the signal has not reached us, though it has not, but because the universe does not contain the fact. One complete and correct account of that person's life ends at a definite moment on their own watch. Another complete and correct account of the same life contains no such moment at all. Both are the whole truth, and there is no third account that adjudicates. This is the point at which the missing quantity stops being a technicality about clock synchronization and acquires a face. And I notice, when I sit with it, that the instinct to resolve it does not go away. Some part of me still wants to insist that one of those two accounts must be the real one, and the other must be a kind of optical artifact. That instinct is not stupid. It is the same instinct that made the twin paradox feel like a paradox, and it comes from the same place. A lifetime of assuming that underneath everything there is a master ledger, a universal running total, a book in which the real elapsed time is written down. The whole content of the last 120 years of physics on this subject is that the book does not exist. Not that it is sealed or lost or written in a language we cannot read. There is no book. And I want to close one last escape hatch before we move on, because someone always reaches for it. The idea that this is an exotic pathology, something that only shows up around objects so extreme that we can safely treat it as a curiosity. It is not. You can produce a horizon with nothing but an engine, an observer who accelerates steadily and indefinitely. No black holes involved, no collapsed matter, just constant thrust, develops a horizon behind them. There is a boundary in space behind that ship, beyond which no light will ever catch up, because the ship keeps outrunning it. Events happening there are permanently outside the accelerating observer's account of the universe. They are not delayed, they are not distant, they are absent. It is called a Rindler horizon, and it requires nothing more exotic than sustained acceleration. Horizons are not a rare defect in the fabric of things. They are what happens when roots stop being able to reach each other, and roots are all there is. Which means the disagreement we have been circling all night is not confined to the edges of the universe. It is the general case, and once you accept it as the general case, you have to look up, because the sky above you is full of it. Part 11. The universe in slow motion. Everything so far has involved a mass, a planet, a star, a collapsed star, but there is a third way to get time dilation, and it does not require any object at all. It requires only that the universe is expanding. As light travels toward us across cosmological distances, the space it is traveling through stretches, and the light stretches with it. That is what redshift is, but the same stretching applies to any pattern in the light, including patterns in time. A process that takes 1 second at a distant epoch is observed here to take 1 second multiplied by 1 plus the redshift. This is not a subtle prediction, it is a direct, testable consequence, and for a long time we had only one clean way to test it. Type 1a supernovae are exploding white dwarfs, and they are useful precisely because they are so uniform. They brighten and fade along a light curve that is close to identical from one to the next, which is why they became the standard candles that revealed the accelerating expansion of the universe in the late 1990s. And when you look at distant ones, their light curves are stretched. A supernova at a redshift of 1 takes twice as long to rise and fall as an identical supernova nearby. At a redshift of 1.5, 2.5 times as long. The stretching matches 1 plus the redshift, exactly, every time. It has been a routine consistency check on cosmology for 25 years. Quasars should have shown the same thing, and for a long time they refused to. A quasar is a supermassive black hole feeding on a disk of infalling matter, and the light coming out of that disk flickers. The flicker is not regular. It is a noisy, irregular, unpredictable variation that comes from turbulence in the disk, and that irregularity is exactly what made it so hard to use as a clock. Through the 1990s and 2000s, several groups looked for cosmological stretching in quasar variability and could not find it. This was not a small embarrassment. It got picked up, occasionally, by people who wanted to argue that the expanding universe was wrong in the first place. The problem was solved in 2023 by Geraint Lewis and Brendan Brewer. They took 190 quasars that had been monitored for roughly 2 decades, observed at several wavelengths, green light, red light, and out into the infrared, and used the multi-wavelength data to standardize the ticking. The variability at different colors comes from different parts of the disk, and once you account for that, the flicker becomes usable as a clock. Then they ran the whole thing through a Bayesian analysis, and the stretching was there, imprinted on every one of them. The headline number from that work is the one worth carrying. At the high redshift end of their sample, at a redshift around 4.5, when the universe was a little over 1 billion years old, the quasars are observed to be ticking about 5 times slower than clocks here. I want you to try to picture what that actually means, because it is easy to file it under expansion effect and lose the strangeness. Hold a stopwatch. Point a telescope at a quasar at that redshift, and watch its brightness flicker. One flicker begins, builds, and finishes. On your stopwatch it takes 5 seconds. 4 of those seconds were added on the way. They were not spent by anything. Nothing weighted them out. They accumulated because the road the light took got longer while the light was on it. At the source, that flicker took 1 second, not appeared to take 1 second, took 1 second. A parcel of superheated gas fell inward, brightened, and cooled, and the whole process ran its course in 1 second of local time in a place that was, at that moment, a little over 1 billion years old. Now widen it out from that one flicker to everything. Every process visible at that epoch, every explosion, every collapse, every orbit, every chemical reaction, the whole physical history of that part of the universe, unfolds, from here, at 1/5 speed. The early universe is not a fast, violent place, seen from a great distance. Seen from here, it is a place where everything happens in slow motion, and there is no vantage point anywhere from which the 2 rates can be brought into agreement. Push the redshift further, and the factor grows. The cosmic microwave background, the oldest light there is, comes from a redshift of about 1100, back when the universe cooled from around 3000 Kelvin to the point where it became transparent. Today we observe that light at 2.725 Kelvin. Everything happening at that moment, if we could watch it, would be stretched out by a factor of about 1100. A second there is nearly 20 minutes here. The oldest thing anyone has ever observed is also, by a wide margin, the slowest. There is no boundary at which this stops. It is a property of the whole sky. It is worth pausing on how much work that one factor does across the whole of observational cosmology. Every measurement of how long anything lasted in the early universe has to be divided by 1 plus the redshift before it means anything. Every estimate of how quickly stars formed, how long a gamma-ray burst lasted, how fast a galaxy rotated 10 billion years ago, carries that division inside it. Cosmologists do not think of it as a relativistic correction. They think of it as reading the units correctly. The stretching is so thoroughly built into the practice of the field that the raw numbers coming off the telescopes would be meaningless without it. The quasar result also has a footnote worth having, because it is a good illustration of how science closes a gap rather than declaring victory. A follow-up analysis published in monthly notices of the Royal Astronomical Society went back over the same territory, paying particular attention to whether quasars themselves change character with cosmic epoch. Whether a quasar at redshift 4 is intrinsically a different sort of object from one at redshift 1, in a way that could mimic or mask the stretching. The conclusion supported the original detection. The gap that had been open for 2 decades is now closed from both directions, and it runs forward as well as backward. Dark energy is accelerating the expansion, which means that in the deep future, the redshift of everything outside our local group will climb without limit. The galaxies we can still see will redden and dim, and their processes will appear to slow, asymptotically, towards stillness. And then they will fade below detection. That is exactly the same behavior as an object falling toward a horizon, playing out across the entire sky over billions of years. The universe develops a horizon of its own, and everything beyond it slows to a stop and goes dark, and there is no moment at which any of it finally arrives. So take the whole picture together, from the last 2 parts. There is a version of this that is only about ships and black holes, and it is easy to keep at a distance. But that is not what the sky is. When you look up on a clear night, you are not looking at a collection of objects existing in a shared present. You are looking at a map of routes. Every point of light in that sky is a different road, running at a different rate, arriving from a different amount of elapsed time, and there is no moment, none, that all of them are simultaneously in. The night sky has never been a photograph. It is a set of separate accounts that cannot be reconciled into one. And that is the thing that finally made this land for me. For most of my life, I carried an unexamined picture of the universe as a single enormous room in which everything is currently happening, with light taking a while to cross it. On that picture, the delay is an inconvenience, an unfortunate limit on how quickly news travels, but nothing deeper. Underneath the delay, the room is there, and everything in it is at some particular moment. There is no room, there are only the roads, and their lengths, and where they cross. Which means we now have everything we need. We started with a body, and went down to a millimetre, and out to a galaxy, and back to the edge of the visible universe, and at every single scale the same thing happened. Clocks disagreed. None of them were wrong. No third number ever appeared. So it is time to answer the question I posed at the beginning, and to say plainly what it is about all this that is far scarier than the twin story lets on. Part 12. What was taken? Here is the answer. Time dilation is not frightening because clocks slow down. Clocks do not slow down. Nothing anywhere in this video slowed down. The cesium beam on the aeroplane was ticking at 1 second per second the entire flight. The muon in the storage ring lived exactly 2.2 microseconds, as muons do. The strontium atom at the bottom of the cloud was not sluggish. Your feet are not running late. Every clock we have looked at tonight was doing precisely what a clock does, at precisely the correct rate, without exception. The frightening thing is what has to be true in order for all of them to be right at once. A route, not a rate. Elapsed time is not a property of the universe. It is not a quantity that exists between 2 events, waiting to be measured accurately or inaccurately. It is a property of a path, the length of the particular road something took between one event and another. And 2 roads between the same pair of events can carry any 2 lengths at all, both of them final, both of them complete, with no third number underneath adjudicating between them. That is the removal. That is the entire thing. There is no total elapsed time, not hidden, not unmeasured, not too subtle for our instruments. It is not the kind of thing the universe has. Before I follow that through, I want to be careful about what is not being claimed, because this is the point where people either overshoot into nonsense or recoil into denial, and neither is warranted. Relativity does not say everything is subjective. It does not say your reality and mine are different, or that truth is a matter of perspective, or that the universe is fuzzy. Almost everything stays exactly where it was. Causal order is absolute. If one event can influence another, every observer in the universe, without exception, agrees which came first, and no frame anywhere ever sees an effect arrive before its cause. The reading on your watch is absolute. Hand your world line to 1,000 observers, and all 1,000 compute the same number. Meetings are absolute. When two paths cross, and two dials sit side by side, what those dials say is a single shared fact. The theory is deterministic and local. Nothing about it is vague or approximate. There was also a serious alternative on the table, historically, and it is worth acknowledging honestly. Lorenz's own interpretation held that there is a real preferred frame after all, that lengths physically shrink and clocks physically slow when moving through it, and that the effects conspire to make the preferred frame undetectable. It gives the same predictions as special relativity for every experiment we can currently perform. It is not crankery. It is out of favor because it requires an undetectable structure to do all the work, and because nobody has ever made it extend to gravity. And every search for that preferred frame, and there have been many, at extraordinary precision, in many different sectors of physics, has found nothing at all. So the escape hatch is genuinely closed. If there were a true rate of time and a true present, every disagreement we have discussed tonight would be an artifact rather than a fact. We have looked for that. It is not there. And once that quantity is gone, several things you have been carrying around your whole life go with it. Start with the largest. We say the universe is 13.797 billion years old, plus or minus about 23 million, and that number is correct, but it is the length of one particular family of roads. It is the time on a clock that has been drifting along with the average expansion since the beginning, and we use it because the cosmic microwave background happens to pick out a natural state of rest that makes the choice convenient. That is a real number, honestly earned. It is also a root length, and there is no fact about the age of the universe underneath it. A clock that took a different road would read something else, and would be equally right. Then there is the present moment, which is worth a paragraph because it follows directly. If there is no universal duration, there is no universal now either. Two people standing next to each other, one walking slowly toward Andromeda and one walking slowly away, will disagree by several days about which moment in that galaxy is happening at the same time as this one. Walking pace. 2.5 million light-years of leverage. Days of disagreement, and no way to say which of them is right, because the question is asking which slicing of space-time is the correct one, and there is no correct one. This channel has spent a whole night on that idea before, so I will leave it there, but notice that it is not a separate strange fact. It is the same removal, seen from the side. Then there is the person at the horizon, for whom the question "have they died?" has one complete answer that says yes, and another complete answer that contains no such moment. And notice how ordinary the mechanism is that produced that. It is not a special rule invented for black holes. It is the same rule that governs the stack of books at Boulder, the millimetre of strontium, the plane flying west, the muon falling through New Hampshire, and the two ends of your own body. Take the identical equation, hand it a heavier number, and the same disagreement that measures 470 billionths of a second inside a person becomes a disagreement with no resolution at all. There was never a point on the way up where the physics changed character. It just stopped being polite. And then there is you. Your age is not a number the universe is storing about you. Nobody is keeping a master count. There is no ledger, no running total, no fact of the matter about how long you have been alive that exists independently of the road you took to get here. What exists is a world line, a path through space-time that started somewhere and has been accumulating length ever since, and the number you would give if someone asked your age is a measurement of that path, and only that path. It is not a report on how much of something you have used up. It is a distance. And your body has been keeping that measurement without being asked. Every cell division, every strand of telomere shortened, every memory laid down, and every one lost. All of it is a physical record of the length of the road you have traveled, and none of it is a record of anything else. Two people who part and meet again have not experienced the same interval with different degrees of accuracy. They have traveled different distances through space-time, and their bodies have honestly recorded the difference. Aging is not something that happens to you at a rate. It is a measure of where you have been. At present, for human beings, that difference is nanoseconds. And I want to be clear that this is a fact about how slowly we move and how weak our gravity is. It is not a fact about the physics. There is no threshold in the equations beneath which the statement quietly stops applying. There is only a threshold beneath which we stop caring, and that threshold is about us. Which brings us all the way back to where we started. Your head is older than your feet. When I said that at the beginning, it was a novelty, a quirk of the body. An odd fact to know, worth about 0.5 of a second over a lifetime. Easy to file away as a curiosity of the physics. It is not a curiosity. It is the smallest possible version of the largest possible fact. You are not one thing moving through time at one rate. You are a bundle of paths, all of them slightly different lengths, and the two ends of you have already parted company by an amount that nothing in physics will ever undo. That was true before anyone measured it, and it will be true after everyone who measured it is gone. The universe does not have a policy for keeping the parts of you in agreement, because there is nothing for them to agree about. And the comfort and the horror in that arrive together, which is what I find hardest about it. The comfort is that nothing was ever stolen from you. The traveling twin was not robbed. The astronaut did not lose 5 milliseconds of life. There was never a universal amount of time that anybody failed to receive, so there is no deficit anywhere, in anyone's account, ever. The horror is in exactly the same sentence. There is no account. The thing you thought you were counting, all your life, was never there. I want to leave you with one more, because it is genuinely open, and it is where the people who work on this spend their time. We have been speaking as though the length of a road is bedrock, as though proper time, the reading on the watch, is the one thing that is definitely real, even after everything else has been taken away. It might not be. The leading approach to combining quantum mechanics with gravity produces an equation called the Wheeler-DeWitt equation, and it has a famous feature. It contains no time. There is no when in it anywhere. The fundamental equation for the quantum state of the universe, in the framework most people have spent the last half-century developing, is a statement with the time parameter simply absent, and nobody agrees on what that means. It has a name, the problem of time, and it has been open since the 1960s. Several serious programs take the obvious next step and treat duration as something that emerges rather than something that is. One proposal has time arising out of entanglement, the universe as a whole in a single static state, with the appearance of change coming from correlations between one part of it acting as a clock and everything else. That has actually been demonstrated in a small laboratory system with a pair of photons. An observer using one photon as a clock sees the other evolve, while an observer standing outside the pair sees nothing changing at all. Another proposal derives the flow of time from thermodynamics, making it a property of a statistical state rather than of the underlying laws. Another replaces continuous space-time with a discrete set of events in a causal order, so that the length of a road becomes literally a count of how many things you pass through. And there is a hard limit that hangs over all of it. Building a clock precise enough to resolve intervals shorter than about 10 to the minus 44 seconds requires concentrating so much energy in so small a region that the clock collapses into a black hole before it can tick. That is not an engineering problem waiting for better funding. It suggests there may simply be no operational meaning to a duration shorter than that, which in turn suggests that the smooth, continuous, infinitely divisible time we have been measuring all night may itself be an approximation to something with no duration in it whatsoever. If that turns out to be right, then nothing in this video was ever about time being distorted. It was about the shape of the shadow that something else casts when we insist on describing it with clocks. I find that possibility oddly steadying rather than distressing, and I have been trying to work out why. I think it is because of the pattern. Every time physics has removed something we assumed was fundamental, the thing that replaced it turned out to be more interesting than what was lost. There was supposed to be an absolute up, and there is not, and what replaced it was the shape of gravity. There was supposed to be an absolute rest, and there is not, and what replaced it was the invariance of light. There was supposed to be a universal amount of elapsed time, and there is not, and what replaced it is a geometry in which the straight road is the longest one, and doing nothing is how you get the most of what you have. Whatever replaces proper time, if anything does, will probably follow the same pattern. It will not be less than what we had. It will be underneath it. So that is why this is far scarier than you think. Not because you might travel fast and come home to a world that moved on. Not because the years could be taken from you. It is scarier than that and quieter, and it is already finished. Nothing is going to happen. The thing has already been removed, and it was removed before you were born, and you have been living perfectly well without it the entire time. Your head is older than your feet, and it always was, and nowhere in the universe is there a number that says by how much it should have been. And if you are lying down while you listen to this, the gradient inside you has very nearly closed. Your head and your feet are at almost the same height, which means at almost the same rate, and for as long as you stay there, the two ends of you are travelling roads of very nearly equal length. It changes nothing. It undoes nothing. It is the closest thing to agreement that the geometry allows, and it lasts exactly as long as you stay still, which is, in the end, a strange sort of comfort. The path of maximum aging is the path of doing nothing at all. Sleep well.